There is a common belief that spaceflight was built on the assumption of success, that missions were planned with the expectation that systems would work, that procedures would hold, and that failure was something to be prevented through careful design and exhaustive testing. That belief is comforting. It is also incomplete. Early spaceflight was not planned around the idea that nothing would go wrong. It was planned around the understanding that something would. The question was never whether failures might occur. It was where they would occur, how they would unfold, and whether the system could survive them without collapsing. Risk was not treated as an anomaly. It was treated as a condition. Spacecraft were built knowing that components would behave unexpectedly, that sensors would drift, that systems would interact in ways that could not be fully predicted on the ground, that human beings operating under stress would sometimes misunderstand what they were seeing. None of this was hidden. Engineering reviews documented it. Simulations attempted to expose it. Training scenarios were built around it. Missions were designed with the expectation that reality would diverge from plan. The goal was not to eliminate failure. The goal was to make failure survivable. This required a very different approach to risk management than the one most people imagine. Instead of asking how to prevent every possible problem, early space programs asked how problems could be contained, how time could be preserved, how systems could degrade without taking everything else with them. A failure that arrived slowly was very different from one that arrived all at once. A failure that could be isolated was different from one that propagated. A failure that left room for interpretation was different from one that demanded immediate action without context. These distinctions mattered more than probability alone. Risk was not measured only by how likely something was to break. It was measured by what would still be possible afterward. Could the crew still think clearly? Could the organization still communicate? Could decisions still be made with enough time to matter? Early spaceflight assumed that some answers would only arrive during flight, that some risks could not be retired before launch. That understanding would be incomplete until systems were exposed to real conditions. This was not a failure of engineering. It was a recognition of reality. Risk management in this context was not about confidence. It was about humility, about acknowledging limits and building systems that could absorb uncertainty without pretending it did not exist. This meant designing spacecraft that failed in specific ways, writing procedures that anticipated deviation rather than perfection, training people to interpret ambiguous signals rather than wait for certainty. It also meant accepting that failure itself would change over time. What was considered acceptable early in a program would become unacceptable later. Familiarity would alter perception. Success would shift risk tolerance in subtle ways. Risk was not fixed. It moved as understanding moved. This episode examines how NASA managed risk when failure was not hypothetical, but expected, how uncertainty was distributed across missions rather than eliminated, how containment mattered more than prevention, and how human judgment became the final layer of safety when systems behaved in ways no checklist could fully capture. This is not a story about avoiding failure. It is a story about learning how to operate when failure was part of the landscape from the beginning, before procedures hardened, before confidence settled in, before success could be repeated. Understanding how risk was managed in that environment reveals something essential about how complex systems survive, not by pretending failure is unlikely, but by preparing to live with it when it arrives. Part 1. Risk was treated as inevitable, not exceptional. In early spaceflight, risk was not treated as a special condition. It was treated as the default state. This is an important distinction because it changes what preparation looks like. If failure is assumed to be rare, systems are built to prevent it. If failure is assumed to be inevitable, systems are built to survive it. NASA operated much closer to the second model than the first. From the beginning, engineers and program managers understood that no amount of testing could eliminate uncertainty. Spacecraft were too complex. Environments were too extreme. Interactions between systems were too numerous to be fully explored on the ground. Risk did not disappear with analysis. It remained. Rather than treating that remaining risk as an embarrassment or an anomaly, NASA treated it as something that had to be actively managed. The question was not whether something might fail. It was how that failure would behave, how quickly it would unfold, and what options would remain afterward. This led to a very specific way of thinking. failures were categorized not only by cause but by consequence. A failure that reduced capability gradually was treated differently from one that caused abrupt loss. A failure that produced clear signals was treated differently from one that created confusion. A failure that bought time was fundamentally different from one that consumed it. Time became the central currency of risk. A system that failed slowly allowed interpretation, communication, and coordinated response. A system that failed instantly demanded action without understanding. The second type was far more dangerous, even if it was less likely. This is why probability alone was never sufficient. A low probability failure that arrived without warning could be more threatening than a higher probability failure that unfolded predictably. Risk assessments that focused only on likelihood missed what mattered most in real operations. What mattered was whether people would have time to think. NASA's risk posture reflected this. Systems were evaluated on how they degraded, not just whether they could fail. Engineers paid close attention to edge cases, not because they expected everything to go wrong at once, but because those edge cases revealed how systems behaved when assumptions no longer held. This focus extended beyond hardware. Procedures were written with the expectation that deviations would occur. Training scenarios were designed to expose crews and controllers to ambiguity rather than clean failures. Simulations deliberately combined problems in uncomfortable ways to see how teams responded when patterns broke down. The goal was not to rehearse perfection. It was to rehearse judgment. Risk management also assumed that understanding would evolve unevenly. Some systems would be well understood early. Others would remain opaque until exposed to real conditions. Rather than delaying missions until every uncertainty was resolved, NASA accepted that some knowledge would arrive late. This did not mean flying blind. It meant planning for partial understanding. Risk was distributed across missions rather than concentrated into a single moment. Early flights validated limited aspects of the system. Later missions built on that knowledge. Failures that occurred early were less dangerous than failures that occurred after the system had become tightly coupled and operationally complex. This sequencing mattered. A problem discovered early could reshape expectations. A problem discovered late could threaten the entire program. Risk tolerance was therefore higher when the cost of failure was lower, and lower when the system had more to lose. Failure was not treated as a moral failing. It was treated as information. That information was not always comfortable. It forced revisions. It exposed assumptions. It revealed interactions that had not been anticipated. But it also reduced uncertainty for what came next. NASA's risk management approach recognized this trade-off explicitly. Eliminating all risk before flight was impossible. Concentrating risk into a single mission was dangerous. The safer path was to expect failure, distribute it, and ensure that when it occurred, the system could absorb it without losing coherence. This required restraint. Not every anomaly triggered redesign. Not every close call demanded immediate change. Engineers learned to distinguish between signals that revealed fundamental flaws and signals that reflected the inherent noise of complex systems operating at the edge of capability. Overreaction could be as dangerous as complacency. Changing systems too frequently disrupted learning. Treating every deviation as unacceptable increased instability. Risk management required judgment about when to intervene and when to observe. This balance was difficult to maintain. It demanded honesty about limitations, patience with uncertainty, and confidence in the organization's ability to respond when things went wrong. It also required accepting that some failures would occur despite best efforts. NASA did not assume success. It assumed exposure. Risk was something to be lived with, not eliminated in advance. That assumption shaped everything that followed. It influenced how missions were sequenced, how systems were designed to fail, and how people were trained to respond when reality diverged from plan. Once failure was accepted as inevitable, the next question became unavoidable. If risk could not be removed, how could it be spread out in ways that preserved time, understanding, and control? That is where early spaceflight focused next. Part 2. Failure was distributed across time, not eliminated. Once failure was accepted as inevitable, the problem changed. If risk could not be removed, it had to be placed somewhere. It had to be sequenced, bounded, and absorbed in ways that did not overwhelm the system all at once. Early spaceflight did not attempt to eliminate failure before flight. It attempted to distribute it over time. This was not an abstract strategy. It shaped how missions were designed, how programs progressed, and how success was defined at each stage. Early missions were not expected to prove everything. They were expected to reveal something. Programs advanced by exposing limited portions of the system to real conditions while keeping the consequences of failure contained. This is why early spaceflight unfolded as a series of incremental steps rather than a single leap. Each mission validated specific capabilities while leaving others intentionally unproven. Some flights tested launch and ascent. Others focused on orbital operations. Still others explored rendezvous, docking, or long-duration exposure. Risk was not concentrated into one decisive moment. It was spread across many. This sequencing mattered because the cost of failure was not constant. Early in a program, systems were simpler. Interactions were fewer. Expectations were lower. A failure at that stage, while serious, was less likely to cascade into total collapse. Later, as systems became more complex and tightly coupled, failure became more dangerous. Dependencies multiplied. Operations overlapped. Small problems could propagate quickly. At that stage, tolerance narrowed. Risk tolerance changed as understanding changed. Early failures were treated as learning opportunities. Later failures threatened continuity. Programs were structured to discover unknowns when the system still had room to absorb them. This required discipline. There was constant pressure to accelerate progress, to combine objectives, to extract more value from each mission. Doing so would have concentrated risk. Early spaceflight resisted that temptation more often than is visible in hindsight. Missions were designed with deliberately limited goals. A flight that appeared modest on the surface often existed primarily to reduce uncertainty for what came next. Success was not measured by how much was accomplished, but by how much was learned without destabilizing the program. This learning was uneven. Some risk retired quickly. Others persisted across multiple missions. Some behaviors only revealed themselves after repeated exposure to space conditions. Thermal patterns, sensor drift, human fatigue, and subtle interactions emerged gradually. NASA's approach assumed this. Rather than demanding complete certainty before moving forward, programs allowed understanding to accumulate through repetition. Similar missions were flown not because nothing new could be done, but because repetition reduced surprise. Surprise was the enemy. A failure that arrived in a familiar context could be managed. A failure that appeared for the first time late in a program could threaten everything. This is why early missions often appear conservative when viewed in isolation. They were not designed to maximize achievement. They were designed to manage exposure. Each mission carried enough novelty to advance understanding, but not so much that failure would be catastrophic. Failure itself was not treated uniformly. Some failures were acceptable if they revealed information without endangering lives or collapsing the program. Others were considered unacceptable because their consequences would have been immediate and unrecoverable. This distinction shaped mission planning. Certain risks were allowed early and prohibited later. Certain maneuvers were attempted only after systems had been exercised repeatedly. Certain capabilities were demonstrated incrementally rather than all at once. Risk was not removed, it was sequenced. This sequencing also applied to organizational confidence. Teams learned not only about hardware, but about themselves. Controllers learned how they responded under pressure. Crews learned how procedures translated into real behavior. Managers learned where communication broke down and where authority needed to be clarified. These lessons could not be learned in simulation alone. They required exposure to real consequences. By distributing risk across time, early spaceflight allowed both technical and organizational understanding to mature together. Hardware behavior and human response evolved in parallel. This reduced the chance that unknown interactions would appear all at once when the system was least able to cope. This approach was not without cost. Progress appeared slower. Achievements seemed incremental. Critics questioned whether more could have been done sooner. But the alternative, concentrating risk into fewer, more ambitious missions, would have increased the chance of a single failure unraveling everything. Early spaceflight chose continuity over spectacle. That choice shaped how programs survived long enough to achieve their goals. Failure, when it occurred, was rarely treated as an endpoint. It was treated as a boundary marker. It defined what was known and what remained uncertain. It reshaped expectations for what came next. This only worked because failures were expected. They were not treated as aberrations that demanded immediate reversal. They were treated as signals that refined understanding. Once failure was distributed across time, another principle became clear. Preventing failure entirely was less important than controlling how failure unfolded when it occurred. That realization led to the next layer of risk management. Part 3. Containment mattered more than prevention. Once failure was expected and distributed across time, the focus shifted again. Preventing failure entirely was no longer the primary objective. Controlling how failure unfolded became more important. In complex systems, the difference between a survivable failure and a catastrophic one is rarely the failure itself. It is how much damage the failure is allowed to do before it is understood and addressed. Early spaceflight learned this quickly. Some failures were tolerable if they arrived slowly. Others were intolerable if they arrived all at once. A system that degraded gradually gave people time to interpret what was happening, communicate across teams, and choose a response. A system that failed abruptly removed those options. Time was the resource being protected. Containment strategies were designed around preserving it. This meant designing systems that failed in bounded ways. Failures were expected to stay localized rather than propagate freely. Firewalls were built between subsystems so that a problem in one area did not immediately compromise everything else. Isolation mattered. If a system could be shut down, bypassed, or allowed to degrade without affecting unrelated functions, the organization retained control. If failures cascaded across interfaces too quickly, control evaporated. This thinking shaped architecture. Power systems were segmented. Life support functions were isolated from propulsion where possible. Communication paths were designed so that loss of one channel did not blind the organization entirely. Redundancy, when used, was often arranged to preserve separation rather than simple duplication. Containment also influenced how systems were monitored. Rather than focusing solely on threshold-based alarms, teams paid attention to trends. Slow changes mattered more than sudden spikes. A drifting reading could signal an emerging problem long before it became critical. This allowed intervention before failure crossed into catastrophe. Procedures reflected this logic. Rather than demanding immediate action at the first sign of trouble, many procedures emphasized assessment. Crews and controllers were trained to pause, gather context, and understand what was actually failing before acting. This restraint was deliberate. Acting too quickly could break containment. Shutting down the wrong system, switching to a backup prematurely, or introducing new configurations under pressure could turn a manageable problem into a cascading one. Containment required discipline. It also required accepting discomfort. Allowing a degraded system to continue operating felt risky, especially when alarms were sounding or performance was visibly compromised. But shutting systems down aggressively often removed options that could not be recovered later. Early spaceflight learned to value keeping options open. A failure that preserved multiple paths forward was safer than one that forced a single, irreversible choice. Containment strategies were designed to avoid cornering the organization into binary decisions under time pressure. This approach extended beyond hardware. Organizational containment mattered as well. Decision-making authority was structured to prevent confusion during failures. Clear escalation paths ensured that issues were addressed at the right level without overwhelming the system. Communication protocols were designed to prevent contradictory actions across teams. Too many simultaneous responses could be as dangerous as no response at all. Containment depended on coordination. Everyone needed to understand not just what they were responsible for, but what they were not. Knowing when not to act was as important as knowing when to intervene. This was reinforced through training. Simulations rarely presented clean, isolated failures. Instead, they combined problems in ways that tested the system's ability to contain them. Teams practiced holding degraded states, managing partial failures, and resisting the urge to overcorrect. The goal was not to restore perfection, it was to stabilize the situation. Containment also shaped how success was defined in real time. A mission did not have to proceed exactly as planned to be successful. If primary objectives were preserved and the system remained intact, secondary goals could be abandoned without shame. This flexibility reduced pressure to push systems beyond safe limits when conditions deviated from expectation. Containment acknowledged that loss could be acceptable. Losing a capability was not the same as losing control. A system could survive with less functionality if it retained coherence. Early spaceflight prioritized coherence above all else. This perspective runs counter to many modern assumptions. It is tempting to believe that the safest system is the one that prevents failure entirely. In practice, the safest system is often the one that fails in ways that are understandable, slow, and containable. Early spaceflight embraced this reality. Preventing every failure was impossible. Ensuring that failure did not overwhelm the system was achievable. Containment was how that balance was struck. Once containment became central, another element emerged as indispensable. Hardware and procedures alone could not manage every failure mode. When systems behaved outside prediction, something else had to absorb the remaining uncertainty. That responsibility fell to people. Human judgment was not a last resort. It was an intentional part of the risk management design. Part 4. Human judgment was the final risk management layer. No matter how carefully risk was distributed and contained, early spaceflight eventually encountered situations that could not be resolved by design alone. Hardware had limits. Procedures had boundaries. Redundancy could only go so far. When systems behaved in unexpected ways, judgment became the final layer of risk management. This was not an accident. Human decision-making was not included because it was assumed to be superior to machines. It was included because it could adapt when systems drifted outside their defined envelopes. Early spaceflight recognized that not every condition could be predicted, and not every response could be prescripted. Judgment filled the gap between what was known and what actually happened. This required a deliberate choice. Humans were placed inside systems that could not guarantee safety through automation alone. That choice introduced its own risks, but it also created flexibility that no purely technical solution could provide. Early spacecraft were designed with limited automation not because automation was unavailable, but because it was difficult to verify across every possible scenario. Automated responses worked well when conditions stayed within tested bounds. When they did not, automation could amplify errors rather than correct them. Human operators could notice subtle inconsistencies. They could weigh competing signals. They could choose not to act when procedures suggested action, or to act when procedures offered no guidance. That discretion mattered. Judgment allowed teams to interpret context rather than follow rules blindly. It allowed them to recognize when a reading was misleading, when an alarm was premature, or when a system was behaving oddly but not dangerously. This capability came at a cost. Human judgment is slow compared to automation. It is vulnerable to fatigue, stress, and miscommunication. It can be influenced by hierarchy, confidence, and expectation. Early spaceflight did not ignore these risks. It worked to shape judgment rather than eliminate it. Training focused less on memorizing procedures and more on building pattern recognition. Crews and controllers were exposed repeatedly to ambiguous situations. They practiced deciding with incomplete information. They learned to articulate uncertainty rather than hide it. This was intentional. Clear thinking under uncertainty is not instinctive. It has to be developed. Early spaceflight invested heavily in creating environments where judgment could be exercised safely before it was needed for real. Simulations were designed to be uncomfortable. Scenarios unfolded in ways that violated expectations. Failures appeared in unfamiliar combinations. Information arrived late, out of sequence, or incomplete. Teams were forced to negotiate meaning rather than execute checklists. The goal was not to produce correct answers. It was to produce coherent decision-making. Judgment also depended on trust. Controllers had to trust crews to execute decisions made under pressure. Crews had to trust controllers to interpret data accurately and communicate clearly. Managers had to trust teams to escalate issues appropriately without overreacting. This trust was built over time. It came from shared experience, repetition, and transparency. Mistakes were analyzed openly. Near misses were discussed without blame. Lessons were integrated rather than buried. This culture was not inevitable. It had to be defended against pressures to simplify narratives, accelerate timelines, and suppress uncertainty. Maintaining space for judgment required resisting the urge to treat procedures as infallible or technology as authoritative. Judgment also required restraint. Not every anomaly demanded action. Not every deviation needed correction. Sometimes the safest choice was to wait, observe, and gather more information. This was counterintuitive. In high-stakes environments, the impulse to act can be overwhelming. Early spaceflight learned that acting too quickly often introduced new risks. Judgment involved knowing when to intervene and when to allow systems to settle. This balance was fragile. Overconfidence in judgment could be dangerous, so could excessive deference to procedure. The system worked best when judgment and structure reinforced each other rather than competed. Procedures provided a baseline. Judgment provided adaptation. When judgment was overridden or marginalized, the system lost resilience. When judgment was elevated without discipline, it lost coherence. Early spaceflight navigated this tension continuously. Human judgment was not treated as a fallback for failure. It was treated as an integral component of the system. Hardware, procedures, containment strategies, and people were designed together. This integration mattered most when things went wrong. When failures unfolded in unfamiliar ways, judgment allowed teams to redefine goals, abandon non-essential objectives, and focus on preserving life and system integrity. It allowed improvisation grounded in understanding rather than panic. This is why early spaceflight often appears to rely on heroism. In reality, it relied on preparation. Judgment was effective because it was trained, constrained, and supported. It was not left to chance. Once judgment was recognized as central, another reality became unavoidable. Risk was not managed by any single element. It was managed by how all elements interacted. That interaction shaped outcomes more than any individual design decision. Part 5. When risk management failed. Despite careful design, disciplined procedures, and trained judgment, early spaceflight still experienced moments where risk management broke down. Not because people were careless, not because systems were poorly designed, but because complex systems fail in ways that cannot always be anticipated. This reality was uncomfortable, and it resisted simple explanations. In many cases, failures did not come from a single bad decision or an obvious flaw. They emerged from interactions between elements that had previously worked well together. Systems behave correctly in isolation, but unpredictably in combination. This is where risk management revealed its limits. Early space programs learned that even well-understood risks could interact in unfamiliar ways. A known limitation might remain manageable until paired with another constraint. A routine deviation might become dangerous when it occurred at the wrong moment or under the wrong conditions. Failure often arrived quietly. Signals were ambiguous. Data was incomplete. Alarms contradicted each other. What looked like noise in one context became meaningful in another. Teams had to decide whether they were seeing the early signs of something serious or a transient anomaly that would resolve on its own. Those decisions were made under pressure. Time was limited. Communication channels were crowded. Information arrived unevenly. Every choice carried consequences, including the choice to wait. In some cases, the system absorbed these stresses successfully. In others, it did not. What made these moments difficult was not ignorance, but partial understanding. Teams often knew the system well enough to recognize that something was wrong, but not well enough to immediately understand why. They faced gaps between what they had trained for and what was unfolding in real time. Risk management frameworks assume that failure modes can be identified and categorized in advance. Early spaceflight showed that this assumption breaks down when systems become sufficiently complex. New failure modes emerged from the interaction of known ones. This does not mean preparation was wasted. It means preparation had boundaries. When failures occurred, organizations were forced to confront uncomfortable truths. Some assumptions had been too optimistic. Some safeguards had been insufficient. Some trade-offs had aged poorly as missions became more ambitious. The response was not to abandon risk management, but to refine it. After incidents and near misses, teams revisited not just technical designs, but organizational behavior. They examined how information flowed, how dissent was handled, how uncertainty was communicated, and how decisions were escalated. In many cases, the technical cause of a failure was less important than the organizational conditions that allowed it to progress unchecked. Silence mattered, ambiguity mattered, deference mattered. When individuals hesitated to speak up, when concerns were softened to avoid disruption, when reassuring interpretations were favored over uncomfortable ones, risk accumulated quietly. These were not failures of competence. They were failures of structure. Early spaceflight gradually learned that managing risk required creating space for disagreement. It required valuing uncomfortable questions. It required systems that encouraged people to surface uncertainty rather than resolve it prematurely. This learning was uneven. Progress came through experience, often painful. Some lessons were internalized quickly. Others had to be relearned across programs and decades. What emerged over time was a more nuanced understanding of risk. Risk was not something that could be fully designed out. It was something that had to be continuously renegotiated. Each mission altered the risk landscape. New objectives introduced new interactions. Old assumptions became outdated. Success itself created new vulnerabilities by increasing confidence and compressing margins. This dynamic nature of risk meant that no static solution was sufficient. Procedures had to evolve. Training had to adapt. Judgment had to be recalibrated. Even then, failure remained possible. This is not a pessimistic conclusion. It is a realistic one. Early spaceflight demonstrated that safety is not the absence of failure. It is the capacity to detect, absorb, and respond to failure before it becomes catastrophic. When that capacity weakened, risk management failed. When it held, systems survived conditions they were never designed to face. Understanding this prepares us for the final question of the episode. If failure could never be eliminated, what did successful programs actually achieve? That question leads directly into the final section. Part 6. What early spaceflight actually taught about risk? Early spaceflight did not solve the problem of risk. It clarified it. What these programs ultimately demonstrated was that risk could not be eliminated, isolated, or permanently controlled. It could only be understood well enough to be lived with. Safety was not a fixed state that systems reached and maintained. It was an ongoing process of attention, interpretation, and adjustment. This was a difficult lesson. It contradicted the idea that better engineering alone could guarantee success. It challenged the belief that sufficient redundancy could prevent failure. It undermined the hope that procedures could fully replace judgment. Instead, early spaceflight revealed something quieter and less reassuring. Risk lives in relationships. It lives in the interaction between hardware and people, between procedures and judgment, between what organizations believe about their systems and how those systems actually behave under stress. When those relationships were aligned, spacecraft survived conditions they were never designed to face. When they drifted apart, even well-built systems became fragile. Successful programs did not eliminate uncertainty. They learned to recognize it earlier, speak about it more clearly, and respond to it with restraint rather than panic. They treated surprises as signals rather than embarrassments. They accepted that confidence must always be provisional. This required humility. It required admitting that understanding would always be incomplete, that models would always lag reality, that experience mattered as much as analysis, and sometimes more. It also required discipline. Risk management only worked when attention was sustained, when assumptions were revisited, and when people were allowed to say, "We don't know," without penalty. The moment uncertainty was hidden, softened, or explained away, the system began to lose resilience. This is why early spaceflight often appears cautious, even conservative. It was not driven by fear. It was driven by awareness. Awareness that complex systems do not fail because they are weak, but because they are misunderstood. Awareness that success can be just as dangerous as failure if it encourages complacency. Awareness that safety is something that must be practiced continuously, not declared once. The most important achievement of early space programs was not that they reached orbit, or even the moon. It was that they built organizations capable of operating inside uncertainty without collapsing under it. That capability did not come from perfection. It came from honesty, from structure, from judgment trained under pressure, and from the willingness to accept that some risks could never be made comfortable, only visible. In the next episode, we will examine another assumption that early spaceflight quietly overturned, the idea that adding more backups always makes systems safer, and why redundancy sometimes introduces risks of its own. Subscribe to continue exploring how space programs actually worked when ideal options were not available. Each episode looks at one constraint, one assumption, and the systems built to live inside them.